All right, so we're going to talk about logarithms today, logarithmic functions. So first thing, we have the common logarithms, and the common logarithms go along with base 10 exponential problems. So they are actually inverses of each other. So here in figure 5.41, they show the graph of f of x equals 10 raised to the power of x. And then in figure 5.4-2, they show the graph of, in dotted, 10 raised to the power of x, but in solid line they have the logarithm of x, which is log base 10 of x. So that's called the common logarithm. So 10, the exponential function y equals 10 to the x. If I tried to find the inverse of it, we would switch x and y. So we'd have x equals 10 raised to the power of y. But we don't have a way of solving that, and so our way of doing that is with logarithms then. So when it's written without any base, it's called the common logarithm. Now, exponential functions have a domain with all real numbers, and their range is where y is greater than 0. And since logarithms are the inverse of exponential functions, then logarithms have a domain that has x is greater than 0 and a range that is all real numbers. Because remember, when we do inverses, not only do when we switch x and y, we're actually switching the domain and range also. So if you look here, it says the log of v is equal to u if and only if 10 raised to the power of u equals v. So the first thing we'll look at here is rewriting them. Okay, so changing from exponential form to logarithmic form and vice versa. The one thing you remember about a logarithm, that it's an exponent. Okay, when I'm finding the logarithm of a number, I'm actually finding an exponent, because if we look at the way these are written, okay, so a logarithmic statement says the log of v is equal to u. Well, that's the same as saying in exponential form 10 to the power of u equals v. Okay, so we looked at similar things to this when we were in Algebra C. So the log of 29 is equal to 1.4624 because 10 raised to the power of 1.4624 is approximately 29. Log of 378 equals 2.5775 because 10 raised to the power of 2.5775 equals 378. So basically, because the base here is 10, I can say that I'm going to take the base here, which is 10, raise it to that power there, and then it equals this thing here. Okay? So 10 to the power of 2.5775 equals 378. So today we're going to look at just common logarithms and natural logarithms, and then tomorrow we'll look at ones with other bases besides 10 and e. So when we solve these equations, and it says without using the calculator find each value, what we're trying to do is say, okay, 10 to what power equals these numbers here. Okay, so 10 to what power is 100,000? Okay, why is it 5? Because there's 5 zeros. Okay, so this is equal to 5. Right, because 10 to the 5th is 100,000. Right. B, the log of 10 is equal to 1. Okay, because 10 to the first power is 10. Letter C, I'm going to change that to exponential form first of all. So the cube root of 10 is the same as 10 to the 1/3 power. Okay. So then this is just equal to, look at Caleb go. All right. Very good, Caleb. Okay, what about letter D? Why not, Eleni? Cannot take the log of a negative number. So there's no solution to this part. Remember, so that's the thing to remember, is that if you look at the graph here, okay, back here at figure 542, that this graph here is exponential functions. The domain is all real numbers. The range is y is greater than 0. This is the graph of basically all logarithmic functions, okay, the basic look of it. And in this case, then, the domain is that x is greater than 0, and the range is all real numbers. Okay? So domain for exponential is all real numbers. Range for logarithms are all real numbers. Range for exponential greater than 0. Domain for logarithms greater than 0. Because they are inverses, so the domain and range switch. So if you try to take the logarithm of a negative number, it can't happen because I cannot raise 10 to a power and get a negative 7. Because 10 raised to any power, whether it's positive or negative, is always going to be a positive number. Now, your calculator will do common logs. Okay? You have that key on your calculator. It says log. All right? That's the key for common logarithms. And so you can use it for, actually, we could have typed all 3 of those, or all 4 of those, we could have typed into our calculator and found the correct answer. Okay? Because we have the common logarithm key on our calculator. And actually, your calculator will do any basis. Just depends on whether you write it correctly or not. So number 2, they want us to solve these equations. Well, to solve a logarithmic equation, most of the time I will change it to exponential. Okay? So if I wanted to change this to exponential, what would it look like? 10 to the 5th equals x. Remember that if there's nothing here, then this is the log base 10 of x equals 5, the common logarithm, which means then that I can say, oops, stay there. That I can say then that 10 raised to the 5th power equals x. So the answer to that is 100,000. And then for letter B, instead of trying to stick that in my y equals to solve it, because the base is 10 here, I can say this is the log of 52 is equal to x. So then all I would need to do is take my calculator, type in log of 52, and I have my number. Now, I want you to think about this for a second. Okay? This is base 10, right? Okay. 10 to the 1st power is 10. 10 squared is 100. Okay. 10 cubed is 1,000. Okay. So, if this number here, so this says log of 52. 52 is between which 2 numbers there?
1 and 2.
Okay, between 10 and 100, right? Okay. So then my answer for this problem is going to be between 1 and 2. Okay. If this said the log of 729, okay, then my answer would be between 2 and 3 because 729 is between 100 and 1,000. Right, so you just type that in your calculator. Okay. Natural logarithms. All right, we were talking about the base e, the natural base e. Well, natural logarithms are inverses of the natural base e. Just like common logarithm is the inverse of 10 raised to the power of x, natural logarithms are the inverses of e raised to the power of x. Because basically what they are is the log base e of x. Okay. So when I go back and forth like we were with, now, let me, before we get there, notice that e raised to the power of x, domain, all real numbers again, range greater than 0. Natural log of x over here, g of x and 5, 4, 5. Okay. Domain greater than 0, range all real numbers. Okay. That's the case for all exponential functions, all logarithmic functions, unless we start doing some shifting around, okay, unless we have horizontal and vertical shifts. So if it says the natural log of v equals u, the base here is e, so then we would say e to the u is equal to v, just like we were with base 10. Just with natural log, we're using e. ln v is equal to u. So with natural log, they use ln, not nl. Okay. I'm not sure of the exact reasoning why, but I'm sure it has something to do with just the way it looks when you write it down. So number 3 just says use a calculator to find these. Nope. Can't take the natural log or the log of a negative number, so hopefully. No. I'm doing the whole thing. How many are there? Okay. All right. But in general, they're pretty easy. So number 4 says solve each equation by using the equivalent statement. So if it says the natural log of x is equal to 2, then we're going to do what? Okay, e raised to the power of 2 is equal to x. So then you just take e and square it.
How many decimal places are we going here?
3 still. And then for letter b, e to x equals 8. And instead of having to put that in my y equals and find an intersection point, then I can just change it from exponential to logarithmic, and it would be the natural log of 8 is equal to x. Thank you very little. All right, so the big thing is here, being able to go back and forth. So these problems that we solved back over here, okay, these problems like here in 13 and 15, problems here at 30 and 36, we could use logarithms, the common logarithm or the natural logarithm to solve them. Okay. So graphs of logarithmic functions. So same thing. Domain, here's just the main points about them. Domain, all real numbers for exponential, all positive real numbers or all numbers greater than 0 for logarithmic functions. The range, exponential, all numbers greater than 0. The range for the logarithms are all real numbers. So you can see where these have switched. Exponential functions and logarithmic functions increase as x increases. Okay, they never decrease. As f of x approaches the x-axis as x decreases, and g of x approaches the y-axis as x approaches 0 for logarithms. Notice that the exponential functions have the point 0, 1. Okay, they both of them, e to the x and 10 to the x. And they both have 1 to the 10th power or 1 to the power of e. And then remember that the logarithms are inverses. So if I have the point negative 1, 1/10, I have the point 1/10 negative 1. Okay. So if you know the points for the exponential function, you can just switch x and y, and you got points for your logarithm. Okay, looking at transformations, we've seen this before, right? C times f of a times quantity x minus b plus d. Right? So we're going to talk about transformations. So remember, we're going to work our way from inside out. All right? So b is a horizontal shift. A is a horizontal stretch or compression. C is a vertical stretch or compression. And D is our vertical shift. So they want us to describe this transformation. We have 3 times the log of x plus 4. Okay, so which letters are represented here by the 3 and the 4? Okay, C and B. So in this case, C is equal to 3 and B is equal to negative 4. Remember, inside the parentheses here with x is always the opposite. So this transformation then is, B tells me it's going to move to the left 4. And then we have a vertical stretch by a factor of 3. So it's going to stretch it vertically by a factor of 3 and move it to the left 4, which means that changes the domain then. Okay? Instead of the domain being greater than 0, the domain is now going to be greater than negative 4 because we moved it 4 units to the left. Okay? So our domain, x is greater than negative 4, and our range is still all real numbers.
When will the range
Never for a logarithmic function. Because it doesn't matter whether you stretch or compress it. It's still going to go on forever. Domain's the only thing that'll change if you move it left or right. All right, number 6. Describe the transformation here, the graph of natural log of x to the graph of natural log of 4 minus x plus 2. Now, one of the things to remember, so if we're using natural log of x, right, so we are basically saying this. We have c times natural log of a times x minus b plus d. Right? So all I did, instead of saying it's just a general function, it's the natural log function. Okay? It has to be written in that form. Is this original we have here, 4 minus x, natural log of 4 minus x plus 2, is it in that form? What's wrong with it, Caleb?
4 minus x.
The 4 minus x is supposed to be x minus 4, right? Or in that order. Okay. So I have to, first of all, change the order. So we've got the natural log of negative x plus 4 plus 2. Okay, there's the first thing I need to do. Okay. Now then the second thing I need to do is I can't have negative x, it has to be x. So we need to factor out that negative. So now, what letters do I have involved in this? We have A, B, and D, okay? A is -1, B is 4, and D is 2. Which means then that, what does A being negative tell us? Correct, okay? It's a horizontal reflection, which means instead of this one going off to the right, it's going to go off to the left then. Okay, so the graph's going to go the opposite direction. So we have a horizontal reflection. Yep, because A is negative. Let's see if I can get it all in here. Close enough. Horizontal reflection, horizontal shift to the left. Or the right, excuse me, sorry. To the right. 4 and up. 2. Just, yep, stretch it or compress it vertically. So, our domain now. Right? So this graph now is, first of all, it was here, right? That dotted line, okay? Now, because of the shift, or because of the horizontal reflection, it's now going to go over to the left as it's moving. And not only that, then, it also, we now have a vertical asymptote here at +4. So the graph is going to go like this now. So my domain is going to be, okay, less than 4. And what about the range? Is that going to change anything? No. That's still all real numbers. Now, okay, the range will never change for a logarithmic function. Just like the domain will never change for an exponential function. Okay? So here's the thing. All right? Whenever domain or range is all real numbers, okay, then those things will never change by transformations. But anything that's restricted, some transformations will change it, others will not. Okay? So in this case, with these exponential and logarithmic functions, okay, if I was to, for the exponential functions, if I shifted it up or down, okay, then it would change the range. Okay? Because right now the range for the exponential functions is greater than 0. So any vertical shifting would change the range. Just like for the domain, or just like for exponential functions, okay, if we shifted it left or right, then it's going to change the domain. And not only that, but I mean, if we do any reflections, it does also. But if it's all real numbers, then it's always going to be all real numbers. No change whatsoever in that. Oops. Okay. All right, number 7. If we invest money at interest rate R compounded annually, then T of R gives the time in years that it would take to triple. So this problem back here that we talked about tripling, all right? All right. So this answer was 13.7 years, right? Okay. So we're going to use this formula to do this for a moment. Is it there? Nope, this one. Okay, here we go. All right. So says, how long would it take to triple an investment of $500 at 5% annual interest? Okay. The only number we need there is the, what, 0.05. Right? This formula only involves the interest rate. Okay? So when we went, so back here at this problem that we did here on number 36, all we need to know that was 8% interest. Okay? And I'm going to show you why. Because if we divided by 5,000, we would get 3 over here. And we take the natural log of 3, and then the same thing over there. Okay. Oops. So the natural log of 3 divided by the natural log of 1.05, 22.517 years. Really, Caleb? So T of R stands for the number of years it takes to triple, and R is your interest rate. Okay? So in question B, it says, what annual interest rate is needed in order for the investment to triple in 15 years? So we have to change this a little bit now. Here we've got 15 is equal to the natural log of 3 divided by the natural log of 1 plus R. So we can do a couple different things, all right? One, we could just plug it in our calculator to find it. All right. Or, let me show you this. Right. Normally, how would I solve that equation?
Multiply by...
Okay, the denominator, right? Okay, we need to get the denominator out of there. So we'd have 15 natural log of 1 plus R equals the natural log of 3. Now, the natural log of 3 is just a number, right? Okay, because you can stick it in your calculator and find the answer. Okay, so that's just a number. So I'll divide by 15. So the natural log of 1 plus R equals, what's the natural log of 3 divided by 15? Okay, so approximately 0.073. Well, now I have a natural log equation. Okay, so how can I get rid of the ln? Okay, I could change it from logarithmic form to exponential form. So we could say that 1 plus R equals e to the 0.073 power. And then subtract 1. And that would be our interest rate. That's for B. You could have done it this way, or you could have just plugged in your y equals and solved for it. It's approximately. .0732408.192. So if I take E, raise it to that power, and subtract 1, we get almost 40%.
Also, just subtract that.
Yep. Oops, wait a minute. I'm sorry. That's not correct. Did you say awkward silence? Sauce. Okay, here we go. -1. There we go. Wow, that even seems pretty high. Is that not right?
Well, you probably took
That seems pretty high. Oh, yeah. All right, let's try this again. Second ln 0.0732480 right? And minus 1 is, there we go, 0.0759, so about 7.6%. Okay, that sounds better than 40% or 50%. So, okay. So working with common logarithms and natural logarithms, so we have 10 raised to the power of x, e raised to the power of x. We're talking about the inverses of them, and just the general switching back and forth. So when we solve these problems that involve base 10, you can either use the logarithms to solve them. If it's in logarithmic form, change it to exponential. If it's an exponential, change it to logarithmic to solve it.